Alright, now we're going to do experiment 11, which is chemical kinetics 2, the effect of temperature on the reaction rate. And so we are going to have 4 different temperatures that we're going to run our iodine clock reaction, the exact same reaction we did for experiment 10. We are going to use for all 4 of these experiments 3 milliliters of our starch, 5 milliliters of the 0.0059 molar S2O3, 5 milliliters of the 0.20 molar Ki, and 5 milliliters of the 0.10 molar S2O8. So those are all of the stock solutions. And each time that we run the reaction, we're going to use the exact same amount of the exact same concentration. All right, so we're going to do the room temperature one again, and so we are going to take 3 mils of the starch, 5 mils of the S2O3, and 5 mils of the 0.2 molar Ki. Now we are going to need an accurate temperature, and so I'm going to use the thermometer. Alright, and so I'm going to use the thermometer and we're going to get our initial temperature. Alright, and so our initial temperature of these reactants in the lab today is 22 degrees Celsius, 22.0 degrees Celsius. Alright, and so now I'm going to add my S2O8 to start the reaction, and I will start my timer. And I'm going to stir this up. Now this is going to be harder to mix in a test tube than it is in a flask. We're going to do all of these in test tubes. Alright, and so I'm going to add this. I'm going to start the timer, and then I'm going to mix this. And I'm probably going to mix this. So there's the stir method. We can take this out. We can do the flick method for stirring. Alright, although it is a thermometer, it's an alcohol thermometer, not a mercury thermometer. Normally you don't stir with thermometers, alright, because they used to be made of mercury. Now we have alcohol, and so we can't stir with them. And this is called the flick stir method. And so I'm going to do a little flick stir method. Alright, so I'm going to do a little flick stir method for about a minute. So each time I mix one of these up in a test tube, I'm going to keep mixing them until my reaction time is 1 minute. So I'm going to try to be consistent on my mixing. And then I will also be monitoring my temperature. So we're at the 1 minute mark. Yeah, so 22.0 is our temperature. Down. And we're waiting for that to turn blue. 22.0 is my temperature in Celsius. Alright, and so we see that it is turning blue. Now for this reaction, we have to make sure the entire solution is blue. It is. We push stop. 1 minute and 45 seconds. 1 minute, 45 seconds. Alright, and so that was the exact same reaction that we did for run 1 in experiment 10, which took exactly 1 minute, and then we said 46 seconds, but I knew it was about a second off. And so we have our reaction. It is at room temperature. At today's room temperature is 22 degrees Celsius. Alright, so now we're going to do the same thing, except we're going to do it in an ice bath. Alright, and so I have my beaker, and it's full of ice and water, and then I put in my 3 mils of starch, my 5 mils of the S2O3, and my 5 mils of Ki in one of the beaker, in one of the test tubes. In the other test tube, I put in the 5 mils of the S2O8. And I left it in here for about 15 minutes so that it would reach the ice bath temperature. And so we have a temperature of 2.0 degrees Celsius. And so now I'm going to mix the two. Get ready with my timer here. All right, I'm going to mix the two. I'm going to start the timer. And I'm going to mix it for the first minute. Now, I want the temperature to stay at an ice bath temperature the whole time the reaction is going. And I'm going to stir this up. Can't really do the flick stir method, can't really do the flick method. I want to keep it in this ice bath to keep the temperature at 2 degrees Celsius. I do not want it to raise in temperature. I want it to stay at 2 degrees Celsius. I may add a few more ice cubes in here. Alright, so I'm going to keep on stirring this until we hit the 1 minute mark. Make sure it is as thoroughly mixed as I can get it. For the stopping point, the whole solution has to be blue, not just the top, not the bottom. All right, so we're at the 1 minute mark. I'm going to get a few more ice cubes. Place a few more ice cubes in there, making sure that this doesn't heat up. Also being careful to not get any water into the reaction. We don't want to dilute it. We want it to be 18 milliliters. So that should do it for our ice bath. And so our ice bath will continue to go. Let's see where we're at on this one. So in this one we have, what we had to do is 10 degrees below room temperature and 10 degrees above room temperature. So I have my cold water solution and I have my warm water solution. All right, and then a rule of thumb for changing temperatures is a 10 degree Celsius change. If you are increasing that temperature by 10 degrees, the reaction is going to go twice as fast. If you are decreasing that temperature by 10 degrees, it's going to go twice as slow. All right, so when we do our 10 degrees below room temperature one, and I'm a little bit off on that, I'm at 9.5 degrees Celsius. So my temperature here is, for the ice bath, was 2.0 degrees Celsius. And then I'm going to also get my ice bath, and I'm going to have my cold water bath going at the same time, because these are a little long, so we can have two going at the same time. I will start my timer on a minute, mark that down, and go from there. So we're at 9.5. So what I'm going to do is, when this timer hits 5 minutes, I'm going to mix these together and put them back into the cold water bath. And since it's I want to raise it up a little bit, bring it out here, maybe I can have a little bit closer to a 10 degree change. Alright, so we are up at the 5-minute mark. Right now we are at 5 minutes. So I put that in at the 5-minute mark. And then I'm going to mix this up for an entire minute. Get back in the ice water. We were still at 9.5 degrees Celsius. I'm going to mix this up for a minute. After I mix it for a minute, I will check the temperature again, make sure it's still at 9.5, whatever it is. On my next reading, that's what we're going to use. Alright, so our reading is actually 10.3 degrees Celsius. So we're getting closer to the, so it was down 11.7 degrees Celsius instead of down 10. Alright. Make sure my temperature here is good. Yep, it is still at 2 degrees Celsius from the ice bath. Again, we started this one at the 5-minute mark, and this one is still running. So when this one turns, I'm not going to stop the timer. I'm going to let the timer go, and I will write down the number that we have when that one is blue. But we're not sure which one's going to change first. But we're not going to stop the timer. We're going to write down the first number, and then we're going to wait and do our hot water last. It will be the fastest. So that one's not going to be near as long as the ice bath will be the longest, and then the cold water bath will be the second longest, and then the fastest is going to be the 10 degrees above room temperature. Alright, and so 7.5 minutes. Alright, so if our rule of thumb is going to hold up here, this should be changing soon. The ice bath should be turning blue real soon. And remember, the entire solution has to turn blue, not just the warmest is going to be where it's touching the table or where the air is getting it in the top. So many times you'll see some blue at the bottom or at the top. And having a thermometer that's blue in there is not that helpful for seeing the color. Alright, the ice bath is starting to turn. Probably can't see it. But I have to make sure the entire solution is the blue color. Alright, so 8:49. At 8:49, the entire solution is blue. 8 minutes, 49 seconds. Oh, and then we have 9 minutes for the ice water bath. So at 9 minutes, it was 9 minutes, 0 seconds. Alright, but we have to subtract the 5 minutes. That makes it a nice simple subtraction. And so we have 4 minutes for the 10.3 degree Celsius cold water bath. Alright, and so now we have our last one, which is the warm water bath, although it's been sitting over there cooling off. It is at 30.9 degrees Celsius. So we're at 30.9 degrees Celsius. So only about an increase of about 9 instead of 10. But all right, and so we'll start this one. So this is going to be pretty fast. All right, so I'm going to mix them. I'm going to start my timer, and then I'm going to put this back in, and I'm going to mix this up, put it back in the warm water, and I'm going to keep mixing it for 1 minute. Actually, I'm going to be mixing it. It's going to, if our rule of thumb is going to be correct, it's probably going to change before the 1 minute or right after the 1 minute mark. All right, so as I'm mixing this up for a minute, really close to the time change that we're expecting. Yes, so 48 seconds. 48 seconds. All right, and so then 48 seconds, we have our final color change. All right, and so that was the experiment, was to do the same reaction 4 times at 4 different temperatures. All right, so let's go look at our calculations for this experiment. All right, so again, we're doing Chemical Kinetics 2. It's the same iodine clock reaction as Chemical Kinetics 1, Experiment 10. All right, so we're looking at the effective temperature. From Experiment 10, we have our balanced reaction, and also from Experiment 10, we calculated the rate law. The rate law is rate is equal to the rate constant K times the concentration of I minus raised to the first times the concentration of S2O8 minus 2 raised to the first. When it is raised to the first, you don't have to put that exponent. A 1 is understood. And so to find the rate, just like we did in Experiment 10, is you take the change in your concentration of S2O3 minus 2 over 2 times your change in time, that is how long it took for it to turn blue. And just like Experiment 10, every calculation that we're going to do is using all of our concentrations after mixing. We did not change any concentration. So from Experiment 10, when we took our S2O3, every time we used it after dilution was 0.0016. That is the same for this one. Our I minus was 0.2 molar. After dilution, 0.056 molar is what we use for all of our calculations. The S2O8 minus 2 was 0.1 molar. After diluting the 3, the 5, the 5, and the 5, so the total was 18, it is 0.028 molar. All right, so what you're going to do is we have our 4 different times. You put them in seconds, and you're going to find 4 different rates. The change in concentration of S2O3 minus 2 is the same for all of them. So final is 0. When the concentration hits 0, the I3 minus reacts with the starch and turns blue. So the final concentration is 0. The initial concentration is 0.0016. All right, and so the only thing that's going to change for all 4 of your rates is the amount of time it took for it to change to the blue color. And so you will have your time in seconds for all 4 of those to give you your 4 rates. All right, and so you're going to have your rate. Now once you have your rate into your rate law, and the concentration of I minus and S2O8, they never change. So you're always going to put in 0.056 for your I minus. You're going to always put in 0.028 for your S2O8. And so you have your 4 rates, and then you're going to find your 4 K values. So your rates, you're going to divide them by your concentration of I minus and your concentration of S2O8. And so you will have your 4 K values. Now K is a rate constant, but it is only a constant at a given temperature. If you change the temperature, you change the rate constant K. So you will have 4 different rate constant Ks because we have 4 different temperatures. All right. Now our temperature has to be converted into Kelvin. And then we're going to have a chart to fill out. And in this chart, you take your temperature that's in Kelvin and you take 1 over that number. And so we want 1 over the temperature in Kelvin. And you will put those 4 data points down. Now you have your 4 rate constant Ks. We just calculated that using the rate law and your calculated rate. You just push the ln of the 4 different K values to give 4 different ln Ks. And the reason why we're doing this is the equation here is the ln K is equal to negative energy of activation over R times 1 over the temperature T plus the ln of A. And that is in the form of y is equal to mx plus b, form of a straight line. All right, and so you're going to plot the ln of K on your y-axis. You're going to plot 1 over your temperature in Kelvin on the x-axis. You will plot the 4 points, and you're going to draw the best straight line using those 4 points. Your line may not intersect any of those points. It may intersect all 4 of them, most likely not. It is going to be the best average line, one straight line, using those 4 points. Now, once you have drawn your line on your graph, you will then have to calculate the slope. Slope is, of course, rise over run. You put 2 points that are on your line. It may not be any of the points that you plotted. You pick 2 points on the best straight line that you drew, and you calculate the slope. All right, now once you have the slope and you have a point, then you can calculate the y-intercept. Now, we have down here that the slope, m, is equal to negative energy of activation over R. And the R value that we're talking about is the 8.314 joules per mole Kelvin, because your energy of activation is going to be given in joules per mole. Now, once you've calculated the y-intercept, which is b in our y is equal to mx plus b, so that is equal to ln A. And it says to calculate A. In order to calculate A, the ln is base E. And so you have your e to the x button on your calculator. And so you will push E to your y-intercept B, and that is equal to the Arrhenius frequency factor A. So A is your Arrhenius frequency factor. Now for the units that you have for K, which you had in experiment 10, exactly the same units as you have in experiment 11. All right, so you'll have to look those up if you don't remember what the units of K are. But whatever units you have for K, they have the exact same units as the Arrhenius frequency factor A. And so you will have to make a graph, and you will have to plot your points and make the best straight line from those points, and then show all of your work on the graph. So when you're doing the slope, I need to know the 2 points that you used. You need to show them and show how you got the slope with the numbers, and then you have a point slope. Then you find the y-intercept, again show that calculation, and then show how you're calculating the energy of activation from your slope, show how you're calculating the Arrhenius frequency factor A from your y-intercept. All of that needs to go on your graph, which also always has to be labeled. And remember to use at least half of your graph paper. All right, don't have a giant piece of paper and only use a small portion of it. Use all of your graph paper. The 4 points should be spread out as far as possible. And that is the end of experiment 11.